Hello, Year 13 doubles. This is a lesson on de Moivre's theorem. It really is, well, I've stated it right here, and I wanted to say straight away, it really is just an extension of this idea, which I'm going to keep repeating in class ad nauseum till you're sick of me. An extension of the idea that when you multiply two complex numbers together, you multiply the moduli, but you sum the arguments, yeah? It's really just an extension of that idea. It's not really much more complicated than that. Now let's take a look at it stated as it first appeared. I've just been looking up actually on Wikipedia, the idiot's lantern, how, where it sat in relation to Euler's formula. And it says here that it was a precursor to Euler's formula. So I presume that de Moivre's came first and then Euler's really wrapped it up, because de Moivre's theorem comes instantly, I would say, from Euler's formula. Now, also in the book, they're very keen. You'll notice if you read through the examples, they're very keen to sort of emphasize, don't assume that power laws work for imaginary numbers like they do for real numbers. They're very keen to keep highlighting that. So we're going to prove things which normally we would just take as obvious because of the way power laws work. And I can actually quickly show you why we can't just assume everything's going to work fine. In fact, no, I'll just talk about this formula a bit more first, and then I'll show you why for certain values it might fail. Now, I've said, open bracket r cos theta plus I sine theta, which is just our typical modulus exponent form, modulus argument form of a complex number. All of that to the power of n simply equals, well, r goes to the power of n, but for the cos theta plus I sine theta bit, there you're going to actually multiply the arguments by n. If I can just give you some intuitive reasoning for that, let's say z is r cos theta plus I sine theta. And let's say we're doing z squared. Well, z squared is z times z, yeah? Now, do you remember me saying, I hope you do by now, that we multiply the moduli? Well, if you're doing z times z, you're going to do r times r, that's r squared, but you add the arguments. So you're going to do, this one's going to have an argument of theta, this one's also going to have an argument of theta, hence you're going to be doing cos of theta plus theta, which is obviously 2 theta, and then same for the other one, theta plus theta, which is obviously 2 theta once again. And there we go. Now, this is simply de Moivre's theorem, isn't it? It's saying, if you've ever got a complex number to the power of n, you need to do r to the power of n, but you need to multiply the arguments by n. It's a way of repeated addition, isn't it? Like multiplication is repeated addition. Hence, if we're doing z cubed, well, that's z times z times z. That would obviously be r cubed, because they've all got a modulus of r, so r times r times r cubed. Remember, multiply the moduli together, but sum the arguments. Well, now this time, this one's got an argument of theta, that one's got an argument of theta, that one's got an argument of theta. So obviously it's going to be cos 3 theta plus I sine 3 theta. So that's to give you like an intuitive understanding of this. It's really just an extension of this idea that we multiply the moduli, but we sum the arguments. So yeah, that is de Moivre's theorem, and it looks like this, and it looks like quite an unwieldy theorem at first, but it's a big part of the chapter. It's going to come up again and again, so we definitely want to make sure we understand it. One moment, I just need to take a sip of tea. Much better. Okay, so that's an idea of why it works. Now, you'll notice I've said here as well, if n is an integer. Now, in the book, they prove it for positive integers, and actually, I'm going to leave it as a bit at the end of the exercise to prove it for negative integers. They also prove it using just the cos theta plus I sine theta format, which is a bit of a shame because, well, actually, just at the end of exercise 8b in the challenge question, they get you to use induction to prove it using the exponential form. Now, this looks even more obvious in exponential form because of the way we're accustomed to using powers. I'll just state this again in exponential form, and you'll think, well, surely that's obvious. Why am I proving that? That's just the way powers work. But you'll notice that they actually say prove this by induction in the textbook. So they're kind of implying there that it's not obvious, yeah? Now, what I get you to prove in the textbook is r e to the I theta to the power of n equals r to the n e to the I theta n. Yeah. Now you might think, well, isn't that obvious? And yeah, I would agree with you. It looks obvious, but you can't assume with complex numbers, and e to the I theta could certainly be complex. Yeah. It's not the r to the power of n that we're worried about. That certainly, because that's a real number. R is taken to be real because it's a modulus. Remember, it's a length. R to the power of n, yeah, that works normally. It's the e to the I theta bit, because that's imaginary. We don't know whether we should multiply the powers yet, but it turns out we can, and we can easily prove it by induction. I'm going to prove it by induction using the exponential form, and then I'm going to prove it by induction, as the book does, using the cos theta plus I sine theta bit. Both are really not that difficult to do. They really aren't. Now, you might wonder, if I can quickly interject here and show you something, you might wonder, why? Why? Surely this is obvious now. You've convinced me, Nichols. Let's move on. It was a good proof. You did like the power to the power. I'm happy. Well, let me just show you why you can't assume that it holds for any value of m. Let's say, and this is just for a mathematical curiosity, let's say that we have n is not an integer. Yeah? Just humour me for a moment. Say n equals a half. We'll take r equals 1, make it nice and simple. We'll say theta equals 0. If you plug this into the left-hand side, this is where it's everything is fine. If you plug that into the left-hand side, you get 1 times by cos of 0, that's 1. I sine of 0, that's 0. And that's all going to be raised to the power of a half. On the right-hand side, we get 1 to the power of a half. And then you get cos of 0, well, that's 1, plus I sine of 0, that's 0. And so you end up with 1 times 1 is 1, 1 to the power of a half equals 1 to the power of a half. All well and good. It looks like it's working, yeah? It looks like it's working. Cool. Well, maybe not. Because what about if I instead used theta is 2 pi? This is where it's going to look like it fails a bit. Yeah, and I'm going to talk about why it's failed, but it's not really failed, but you have to be careful with non-integer powers. Okay, let's say we have these values. Left-hand side, we're going to get 1 times cos of 2 pi, which is once again 1. Sine of 2 pi is 0. And then we're putting that to the power of a half. Cool. So that looks like the same as before, basically. But on the right-hand side, what do we get? We get 1 to the power of a half. And now we're doing cos of a half times 2 pi. And that's cos of pi. And cos of pi is minus 1. Sine of pi is still 0. And so we end up with 1 to the power of a half equals 1 to the power of a half times minus 1. Now, that on the face of it does look like a mistake, yeah? But it depends on your way of thinking. It's actually because it's a multi-valued function. Because remember, 1 to the power of a half is the square root of 1. And if we treat 1 to the power of a half here as positive 1, we get positive 1 times minus half, which is minus 1. And that is actually kind of a root of square root of 1. But it gives it a multi-valued function. And it's the reason why we have to be super careful when we talk about m, m being like a fraction, or even n being complex. It does kind of hold. It does kind of work when n is fractional or when n is complex, but it gets a little bit more, tricky, and it can certainly lead to some errors. So, yeah, you've got to be careful and cautious with it. Anyway, let's get on with the questions. Well, firstly, what I wanted to do was prove the result by induction, just in case you get asked to prove the result by induction. Now, proving it with the exponential form, it happens to be asked that question at the end of the last exercise in the challenge section. So let's just quickly do it with the exponential function, which I would definitely use if I had the choice. I'd just say let, e to the I theta. Well, as well, I'd say note, note e to the I theta. If it didn't explicitly say you can't use the exponential function, which it does actually in the challenge question at the end of exercise 1c, well, what would we have? Well, firstly, I'd just say, obviously, e to the I theta. Oh. Feels silly saying obviously e to the I theta is cos theta plus I sine theta. It's like, is that really that obvious? But I proved it to you that in the original video. So what we've got here is r e to the I theta to the power of m equals r to the n e to the I n theta. Yeah? All we've done there is replace theta with n theta. So clearly it should hold, this idea. It really should hold. And then you can put the r's in afterwards. Okay, so base case. Let's prove by induction. N equals 1. And when n equals 1, it clearly holds. In the exam, I might even write left-hand side equals this, right-hand side equals that, just to make sure they're not going to stitch me up on the base case. But the base case clearly holds here, because the left-hand side is obviously going to be identical to the right-hand side. Okay, assume true for n equals k. Then what are we going to have? We're going to have i.e. re to the I theta to the power of k. It's dead easy, this proof by induction. It's not hard. You don't even have to worry about memorizing it or anything like that. Just remember, it is actually quite straightforward. Okay, then for n equals k plus 1, let's pan down a bit. We have, okay, let's do the left-hand side, re to the I theta to the power of k plus 1. Equals, remember you've always got to use that which you assume to be true. So we'll write this as re to the I theta to the power of k times re to the I theta to the power of 1. Now you might say, oh, Mr. Nichols, you said you can't just be, you can't just apply index laws to imaginary numbers the same way you apply them to normal numbers. But do you remember we actually proved in exercise 1b that this was true, that if you have e to the I theta 1 times e to the I theta 2, then that's going to be equal to e to the I theta 1 plus theta 2. We've already proved basically that you sum the arguments. We've already proved that, yeah? So we're absolutely allowed to write e to the I theta, re to the I theta to the power of k plus 1 as re to the I theta to the power of k times by re to the I theta to the power of 1. That's absolutely fine. And so we can now use our assumed result, which was that is the same as rk e to the I k theta multiplied by r e to the I theta. We can certainly do r to the power of k plus 1 here because r is real, so we've got no problems, applying normal index laws there. And like I just said, we can sum the powers here because we've already proved that we can sum the powers when you've got e to the I theta 1 plus e to the I theta 2. K theta and theta are clearly real, so we can use them in the normal way. And you're going to get I theta times k plus 1, which is the result with k plus 1 substituted for k, and so we just need our inductive remarks, something along these lines of, but this is the result with k plus 1 substituted for k. Sorry for my handwriting. Hence, true for n equals k and try applies true for k equals k plus 1. Hence, true for all members of the natural numbers by induction. I don't know why I'm not just writing n of n by induction. Done. Yeah. Now, I tell you what, I feel like I feel like the book makes a bit of a meal out of the proof by induction for the cos theta plus I sine theta. It's really exactly the same as the one which was originally in the AS book, proving that you can sum the arguments. It's the addition, well, they call it the addition formulae. I call it compound angle formulae, where you sum the angles, the cos theta sine theta plus sine theta cos theta. I did a proof of this just in the other video, just in the other day, I think. So I don't think I will prove that, actually. It seems like you've got it in the book anyway. Please do contact me on the Maths Help Desk if you want to talk through it. I'm very happy to talk through it. Okay, so let's do a couple of examples. The examples are actually pretty easy to use. I don't think the next exercise, which is at 1C, will stress you. Can I say as well, I don't think you should do every question in 1C. It gets a bit samey. I think you should do every other one. You do want to get used to this. And I want to show you straight away one, just like I'm going to use the example 8, which they do, because I think they really stress with it too much. And I think, no, that is not a difficult one to do. 9 pi over 17 plus I sine. Ooh, 9 pi over 17 to the power of whatever, 5. We're going to simplify this. Yeah, so let me write simplify. Then we've got on the bottom cos 2 pi over 17 minus I sine 2 pi over 17 to the power of, what is it, 3 or something like that. Cool. Okay, now, yeah, this example is in the book, but I just want to mention a couple of things. Firstly, why is this one a problem? It's the minus on the bottom. You always want it as cos of a value plus I sine of the same value, and it must be plus, but it's easy to fix that. We can use this trick. Cos of minus x is exactly the same as cos of x, and minus sine of minus x is the same as sine of x. So what we could do is to make that minus a plus, we could actually rewrite this one if you like, make it sine of minus x is minus sine of x. Yeah, and so as that's minus sine of 2 pi over 17, I could change it to positive sine of minus 2 pi over 70, which is the same as the bottom one on the left-hand side. So let me just show you what I mean. Let me write it down. So on the top, straight away, we can start using de Moivre's theorem, which says whatever the power is, just times it by the arguments. So we're going to get cos of 45 pi over 17 plus I sine of 45 pi over 17. And as it says in the book, it's way easier in exponential form. It's actually less work. It really is. But you've got to rewrite the bottom either way for both of these things. Write it as cos of minus 2 pi over 17. And this has come up in the other exercises anyway, so I'm sure you've noticed. Plus I sine of minus 2 pi over 17. And I'm still going to have to put that to the power of 3. Now let's actually start writing this in exponential form. As it points out in the book, it's much easier in exponential form. If given a chance, I would always way rather write down this, which is just e to the I. I suppose the only reason it's not messy is because you've got the I there, I times 45 pi over 17. At least I only have to write that down once though. On the bottom, I'm going to have e to the I times by minus 2 pi over... Oh, now don't forget, I've got to do that times by 3, so minus 6 pi over 17. Almost missed that. And then what I can do is just subtract the arguments to give me e to the I times... Right, 45 minus minus 6 is 51 pi over 17, which is actually e to the 3 pi I. Now, remember what I said the other day? I was really faffing about the other day saying why that's the same as that. Just add or subtract multiples of 2 pi. I looked a video back which I made for you the other day and I thought, what am I waffling on about? So yeah, sorry about that. You can always add or take away multiples of 2 pi from these things because it works just like a clock, yeah? It's basically going to basically repeat every 360 degrees. And so what you've got is e to the pi I over 17. Pi I, sorry. And then what I could do is just write that as if you want to see it real clear why that is actually minus 1, well, let's actually write it down go back to complex number format, e cos of pi plus I sine of pi. Well, that's obviously minus 1 because that one's 0. And there we go. I think they make a bit of a meal of it in the book. I really do, but maybe you think they actually explain it better. So I don't know. Okay, so that's one example, and you'll be doing that a lot in the exercise, so you will get used to that. Another example is, and these ones are more awkward in many ways, I'm going to do question 5 from the exercise. So feel free to skip this one. Or pause it now, as I always think this is a good suggestion. Pause it now after I've written it down anyway, and you can try and do it on your own. What about if you had 3 plus root 3i, or as I put it here, I root 3, just so it doesn't look like the i's in the square root, to the power of 5. We want to simplify that, or write in the form a plus bi root 3. Now, your calculator, if you put it in complex mode, will do this straight away. 1 second, gulp of tea. Much better. Oh, it's going cold. I've been speaking for so long. I must finish this off. Okay, so if we're doing something like this, we really need to go to modulus argument form. It makes things so much easier because de Moivre's applies to anything which is in modulus argument form, which the exponential form kind of is. So you can use it with the exponential form, but you can't use it with the Cartesian form. You've got to convert. So let's actually think about what this complex number really looks like. It doesn't hurt to just quickly draw a very quick nav sketch in the Argand plane. It's in the first quadrant. It's 3 across on the real, root 3 there. We could easily find r for that complex number by using Pythagoras. We get root 12, which is 2 root 3. We could also find the argument, and they tend to give you ones which are nice multiples of pi, or they often do anyway. So tan theta here is root 3 over 3, which is 1 over root 3. I think that's pi over 6. Pretty sure that's pi over 6. Yeah, pi over 6. Okay, cool. So, because it's 30 degrees. I feel more on the ball tonight, you might notice that. Okay, so what are we going to do? We're now going to rewrite this as this equals, now we know what the complex number in here is in modulus argument form. I can write it as 2 root 3, and you'll probably like it as a, well, do you want it in e to the I theta format? Maybe it's just nicer in e to the I theta format. E to the I pi over 6 to the power of 5, which equals, right, we've got to do 2 root 3 to the power of 5. That's actually quite difficult. It's easy to mess that up. 32 times 9 root 3, and 32 times 9 root 3 is 320 minus 32, 288 root 3, I think. And then we're going to multiply the power there. Just the nice thing about exponential form is it works exactly the same way algebra's always worked. E to the 5 pi over 6 times I. Make sure it's been times by I. And that's now, to convert it back to Cartesian form, it's always nice to see it in the cos theta plus I sine theta format, because you can just work it out. So we've got cos of 5 pi over 6 plus I sine of 5 pi over 6. And then you just got to work those out and find out the values, basically. I think cos of 5 pi over 6, what is that? Oh, it's the same as the negative of cos of pi over 6. And so minus root 3 over 2. And then that one's going to be a half plus I over 2. Multiply it out. Is that 144 times 3 minus 432? 144 times 3. Sorry, I'm just going back to the old days, eh? 4 times 3 is 12, 13. 1 times 3 is 3 plus 1. 4, 3, 2. Why did I doubt myself? And then minus, plus, sorry, 144 root 3i. And hopefully that is correct if we check the back. Let me quickly check the back. Yep, it's good. It's good. Thank God for that. And that is the way demoivres can be applied. Okay, I'd like you to do pretty much all of exercise 1C, but missing every other question, if you know what I mean. Particularly questions 5 to 9, or I've just done 5, 6 to 9. And try the challenge. Try the challenge at the end, where you've got to prove or basically Demoivre's theorem works for negative integers as well, because it does. It works for negative integers and positive integers, and all I've proved so far is positive integers. Okay, I hope that was helpful. Have a good go at exercise 1C. Don't forget as well, I'm collecting in the proof by induction homeworks at the moment, so do submit that online, because I'd like to start marking that at the weekend. And yeah, keep up the good work. Well done. Okay, bye-bye.